And we are live. Welcome, folks. Welcome to I Can Science That, part 2 of the AMA that we did last time. Troubling Tribune is today's guest. Troubling was unable to make it to the last one, and so we're doing a little catch up here. So you want to tell folks a little bit about yourself, maybe shout your channel out?
Absolutely. First off, I'd like to shout you out. I Can Science That. Thanks for the platform. Thanks for having me on such short notice. I apologize for missing the last one, but you had some great guests, some great conversations on the last one anyway. So anybody who hasn't checked that out, definitely go and do so. Anybody who doesn't know who I am a content creator over here on YouTube, Rockfin, TikTok, Instagram, etc. You can check me out on any of the platforms, but I prefer the long form over on YouTube and Rockfin. And you can find me right under here, my channel name, Troubling Tribune. So I appreciate anybody who wants to go check that out, give your honest opinions, reviews, whatever value you can get from that. I cover all kinds of contentious topics like religion, philosophy, a lot of flat earth stuff. So if you like that kind of thing, go ahead and check it out. As far as the main purpose of why I'm here, the main questions that I have, they pretty much revolve around, and I'll start with the gas pressure. I know some people might be groaning or sighing. It's like, man, we talked about gas pressure so much on the last one. And
I'm going to try and do better this time.
I could definitely appreciate that. But I just feel like there was some things that kind of seemed a little vague or unanswered, and I'd like to get, a lot more clarification on. So I guess
All right.
if now's as good a time as any, I'd like to go ahead and fire my first question.
Okay, let's just tell people a little bit about, oh no, gas pressure. Let's a little bit about what we're going to try and do. This time, I'm going to try and run a little timer here. Let's do 2 minutes limit for the question so that we are just asking a question. And then I'm going to try and give you a 2-minute answer, just like TLDR, this is the deal. And then you just ask me clarifying questions and we'll discuss it until we can get to, either we get just totally stuck or we get to some kind of understanding. And then we'll go on to the next question. Cool?
Awesome.
All right, so fire away. What is your first question?
Okay, so my first question is going to be in regards to just kind of a jumping off point to reset a little bit. It's going to be in regards to the gas pressure gradient that we have next to the expanding or unexpanding. I'm not sure what you believe in on that, or what science says exactly these days with the nature of space, but it is a massive vacuum. I know that last time when Jaron was on, it was brought up that the pressure gradient would basically equalize and create a new gradient in the box, in the theoretical box that you guys were talking about. So I guess to isolate the question, I would ask, what is the formula or scientific equation that can tell us the exact rate at which something should dissipate when it comes to gases?
Okay, so what is the exact rate that something's going to dissipate in terms of gases? All right, here we go. I would go to this one. Hold on, I got too many tabs. Must be doing high IQ research. I got so many tabs open. Present screen, and let's do that one. Okay, I would say my go-to on that is the Navier-Stokes equation. That's the one that they kind of beat into us. And let me throw this. Hold on, my timer isn't running. I want to make sure I don't go to go. So let me throw this in the chat for people. It's just a link. Navier-Stokes equation describes the relationship between flow and pressure and stuff. If you know some things about the velocity of your fluid, and velocity and the viscosity and so forth, and you'll see density times gravity sitting there in the equation. I don't know if you guys can see my mouse.
It's pretty small.
Highlight that.
Oh, let me try to blow up my screen.
Boop, 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 boop. Here we go. The famous Navier-Stokes equation, and can be expanded as so. So basically, this is going to relate the change in pressure to the change in velocity and the force of little g there. So I guess that's my TLDR to your quick question. How do we know how the flow is going to go? The flow is going to be determined by the delta of pressure, the current velocities, the viscosities, and of course, gravity.
Okay. Pretty straightforward answer. Obviously, lots of factors to take in there.
Yeah.
So let's go ahead and clarify with this even further. So when it comes to all those factors that you just mentioned, and maybe I just missed it because there was a lot. Does anything with that have anything to do with the amount of space that needs to be filled for the pressure mediation? Like, for example, when we talk about the Jaren's box example, we have the small one that's sealed with a gas pressure gradient, and then a larger, possibly room-sized one that is vacuumed out with a much lower pressured gas pressure gradient, I believe we'd call it, because there's always going to be some pressure available when there's gases present. We can't suck them all out.
Okay.
So
What I was trying to answer with this one was, what's the flow rate, as opposed to like, what's the ultimate steady state result? And so because we are talking about flow rate, the volumes don't go into the equation. It is dependent on the pressure differential at the point of flow that you're looking at. So, like, for example, you have a container and you open the lid. The top of the container is where the flow is going to occur. So we would look at the pressure differential across that opening, and then we could plug it in and see what happens. How fast will the air flow in or out of the vessel? So that's why you do not see volume in here, because it doesn't say like how long does it take to empty the container. Isn't in this equation. This is the how fast does the air move. Right.
gotcha. So that's that's a bit some variations in the equations to get the different answers for, I guess, the questions that we would have. Because I'm obviously trying to extrapolate this out to the bigger room being the entirety of outer space, at least that we know of, and then the smaller box, of course, being the Earth. So, with that being said, and just to make sure that I have clarity on the flow question or the flow point that you just made, so you're saying that the point that the transfer actually occurs is really the only point that we look at to determine the total flow rate.
So far, that's the equation that I'm showing over there, is one that shows the flow rate. That equation doesn't instantly give you the equilibrium point all by itself. But to get the equilibrium point you're looking for, that's when the flow rate is 0. If there's no flow across the barrier, the barrier, or the the opening, if there's no flow across the opening, now you're at equilibrium.
Yeah, that makes sense. So I'm with you so far.
All right. And so I do want to stress again, you'll notice there's no volume in that equation, and we don't need to know the volume to tell you that answer. What we do need to know is the pressure differential, and the velocities, the viscosity, the density, and gravity. We can tell you, if you plug those in, you'll see gravity is sitting in there. And so in order to make it 0, you're not going to get a 0 flow with a 0 pressure differential. And the gravity has to be accounted for.
For clarity's sake, when you say gravity, do you mean the the actual like mass attracting mass equation, or do you mean just the acceleration average?
That's just an acceleration in that equation. We make no, I've as yet made no claims about where that comes from, simply that there is an acceleration term sitting there with a G on it.
Awesome. Okay. So that definitely helps with that. All right. So moving on with it, just again to make sure that I'm in full understanding, even though we're only looking at the one point that um, the the point of transfer, I guess, for the total or for the fastest part of the flow. When I'm looking at something totally right, like to put an example of like a garden hose, obviously it's not just one part of the water that's moving; it's all the water that's in the hose moving through. And I know the pressure for that's a little bit different, but basically what I'm saying is kind of like with the example again, go back to Jaren's 2 boxes example. Once the pressure at the top that's closest to the vacuum or closest to the low pressure begins to flow, wouldn't it also be true that as soon as that pressure closest to the lower part of the gradient becomes lower, that the heavier and lower part of the gradient would also flow up or towards the point of low pressure to continue that equalizing process, I guess.
Okay. Hold on just a second. I'm getting my member. There we go. Get my Discord on here. There was a request for my Discord, so let me throw that on there. Just for peeps that want to connect on Discord. So yeah, what you just described, I think is basically right. At any point, you could say like, here's the pressure here, here's the pressure here. Is there going to be a net flow from this point to this point? And you plug that in, and depending on the density of your gas and the force of gravity at that point, I really shouldn't call it force of gravity. Let's just call it that acceleration that's in there, right? That G acceleration that should predict whether there'd be any flow at that point. And what we see is that it's a very tiny effect because the density is very low for gases in general. And so the amount of pressure differential that you can sustain varies by height, right? A small height has a very small pressure differential, and the amount of it is going to be based on the gravity vector and the density of that gas. So at any point, right, according to that equation, at any point in our volume of air we're looking at, there will be, like from here to here, there's a small pressure differential. It's slightly lower pressure here than it is here. And it's, each time you go up, that continues. Does that make any sense?
Yeah, I'm pretty familiar with the concept of like how the gradient works.
Right. So I wonder if let me try this approach. This is what I was trying with Jaren the other day. Didn't go well, but let me try this. Let's see. I want to share this. Are we seeing this? Yeah. Okay. Let's do a thought experiment together. Now, I heard this one time and I love it. A thought experiment does not tell us what the real world is. A thought experiment tells us what we think the world is because it's happening in our own thoughts. Does that make sense? So we'll use a thought experiment to explore your own logic, your logical process, and ensure that you are following logic as we go. Does that make sense? All right, so here we go. This is thought experiment. This is the one we tried with Jaren. Imagine a tall pipe, right? A pipe. It's closed at the bottom, but it's open at the top. And this pipe is so tall that it's 14.7 psi at the bottom of the pipe but the air around it drops in pressure as it goes up. So the top of the pipe is at 14.6 psi. So the pipe is tall enough to lose 0.1 psi through the gradient. Does that work?
Yeah.
And we understand that there will be no flow. The air isn't going to get sucked out of the bottom of the pipe, even though there's a pressure differential. That the weight of the air is causing it to be higher pressure at the bottom and lower pressure at the top.
And you're saying, and again, the tube is open at the top, but the
It's
gradient
open.
on the
Yeah.
outside is the same.
Yeah,
So,
exactly. The gradient in the world is there. We know that's true, right? So if I just drop a pipe in the world, the gradient will be the same inside the pipe as it is outside the pipe.
sure.
Okay, so great. Let's make a taller pipe. This pipe runs like up a mountain. This pipe is so tall. So tall that the top of the pipe is now 10 psi. Because it's exposed to the air, and the air at the top of the mountain is 10 psi. Right?
Okay.
So here we have a pipe, and the bottom of the pipe is at 14.7. Top of the pipe is 10 psi. There's no air flowing within the pipe, and there's no net exchange between the top of the pipe and the air around it because they're both at 10 psi.
Sure.
Sure.
And then you extend it all the way out until there's basically no pressure.
Let's go to 1 psi. Same rules apply. Our pipe still shows no flow. Agreed?
Sure.
0.1 psi. Will there be flow now? Or will it just be stable in a column of air, 14.7 at the bottom, 0.1 at the top?
Yeah, if all the conditions are the same, then I agree with you. I mean, if the gradient's the same on the outside of the tube, then I mean, it's not going to have any. There's not going to be anywhere to flow to.
Okay, so let's keep going. How low can we go before suddenly the air is sucked out of our pipe?
That's actually the question that I'm trying to figure out.
Well, we agreed it did not get sucked out at 0.1 psi. Is it going to get sucked out if we keep going up until the gradient drops it to 0.01 psi?
I mean, I suppose not. But the thing that I
Well, there you go. So that's the point of this thought experiment. It shows that based on your own understanding of simple logic and your own understanding of how the air works in our world that we see every day, the air does not get sucked out. So,
well, the only issue that I have with that, and it basically goes with the begging the question part of it, is that in the scenarios that we have in the real world that are in controlled examples, I mean, they're in enclosed containers where we have this gradient. The pressure gradient antecedent, sorry, I'm saying it wrong. The pressure gradient actually needs a pressure to all, or sorry, a wall to all work off of.
okay, you're
So I
getting the
know
quote
that
wrong. You're supposed to say
all good.
a container is the necessary antecedent. That's the Nathan Oakley quote you're going for there, isn't it?
I'm not trying to be a parrot, right?
Okay. Well, I mean, the fact is there is no such thing as this necessary antecedent. It's just made up by some propagandists who want to say that. That's all. There's no thing like that. No.
So again, the issue that I have is that in the real world, the systems aren't, in this perfect, unmoving, unchanging column. We do have,
Sure.
even according to mainstream, I'm pretty sure, correct me if I'm wrong, we have flow going on between, or a dynamic pressure system occurring. So
Absolutely. Does that change our basic understanding? I mean, where we're starting from is why does science tell us that the air should not get sucked off of our atmosphere, off into the vacuum of space? And you ask, why is that? This is why that is, and you know it. And that's really my point, is that you already know this. So why are you asking this question? Does wind mean this isn't true?
No, what we struggle with, and I'm sure I'm speaking for a lot of people, is the extremes in the difference of the pressure. And then I know that you say in the equation the volume doesn't have anything to do with it. But the thing that we always go to, and again, this is why I'm here to try to broaden my understanding, is that we have a huge room, right? We don't know how big space is. We just have a um, idea of how far we think we can see of it, and so we think that the known universe is this big, but it can possibly be bigger than that.
Yeah,
So
that's right.
in comparison, I mean, if we want to put it to scale to Jaren's box example, what
Right.
we have is a pressure gradient in a tiny box that's open next to a massive, if let's try to scale the box. If the box is the size of a marble, I mean, the room for space would be it's freaking absolutely massive. I'm trying to can't even wrap my head around it. It's huge.
Right.
The
Space
universe
is huge. Space
space
is
is
huge.
absolutely huge, right?
Space is
So
huge.
the reason why we have the problem is that the pressure gradient equalizes itself out to the actual room in the example, right? So you have low pressure at the top of the room,
When
which
you
has a lid.
scale this down, the numbers don't scale, right? That's kind of what you're saying? You can't make a scale model of our pipe and have it still work.
Well, I don't know. That's why I'm asking for the mathematics.
You can't. And the reason you can't is because that flow rate that I did show you earlier was dependent on rho and G, right? And you're not scaling those down. So when you scale down and make your little marble box or whatever, we're still dealing with the G from the world around us. And if you could scale G up appropriately, you could make an acceleration thousands and thousands of times more powerful than normal G. You can, and we do, scale this experiment down. And everybody does that all the time. And this is another thing I tried to explain to Jaren, which is that's what a vacuum pump is. A vacuum pump, inside the vacuum pump is an extreme pressure gradient. Agreed?
Yeah.
How does it do that? It does it by applying a force to those gas molecules. And it's not going to use G, it's going to use some other mechanism, right? So for example, I like to use the example of a centrifugal pump, a turbine. It spins, and the centrifugal force shoves the gas to the outside of the spinning rotor. And that creates a pressure gradient where you have low pressure at the hub and high pressure out at the outer wheel. And that's the same thing. We've just used a force much, much larger than that G that's in that equation naturally. Like our environment provides 1 G of force, but if you crank up a turbine to thousands of RPM, you can get a much larger force out of it and get a compressor.
So far, so good. And I definitely, like I said, I'm pretty familiar with the idea of how the gradient works and the idea of, um, low pressure and high pressure and the reason why all that works on a basic level. I may not know the exact equation behind the flow rate behind it, but that doesn't mean that I don't know that that's how it works. It's pretty
Well,
obvious.
and that's my main point that I like to make. You don't need to know the Navier-Stokes equation. You don't need to apply it. This what we have on the screen is fine. That's enough. It's enough to recognize that when we go outside and we drive up and down a mountain, the pressure changes. So we know for a fact that there is a pressure gradient in our atmosphere. So
So that part's not really the part of contingency, right? I think that
Well,
most,
the contingency is that something happens in your mind where you don't naturally extend it to 0.0000001 on your own, right? But if I walk you through it, we can get to 0.00001 and we agree, yeah, that's a pressure gradient. Why did you have a mental block getting there before? And is that mental block still up?
so where my block is, if you want to call it that, and again, this might be my hang up entirely, right? That's why I'm here. So it's that even in the scenario that you painted with the tube that's open at the top, right? I'm still thinking that it's in the world that I mean, we have two completely different assumptions about the way that it works. You assume that at the top there is that the gradient goes all the way up to, um, very, 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 very tiny, so small to the point where it creates a um, tremendous torr. I mean, I don't know what the exact number is for the torr of the vacuum of space, but I
Mhm.
mean, there's definitely a force created there because of that pressure differential. And
Okay.
so um, and this is why I'm trying to ask for the actual mathematics to see if anything, to see if it actually
Let,
checks out.
let me hit you. Let me hit you with a simpler piece of mathematics that I think really, hopefully, will be eye-opening, and that is the tremendous torque and the giant force that you're speaking of. I think many of us have the idea. We are definitely told and shown in popular media that exposure to space is a tremendous force. We see sci-fi movies where people explode when they get pushed out the airlock, right? Okay, that is not accurate. What science actually says, and you've heard me say pressure differential a few times, right? Pressure is force per unit area. That's why I like to use PSI, not just because I'm an American, not just because they're freedom units, but they say what they mean. Pounds of force per square inch. You with me?
Sure.
So, so pounds per square inch, that's force per unit area. That's an equation. So how much force? Let's say I have the vacuum of space on one side and 14.7 psi on the other side. And I have a 1 square inch hole in between them that I'm going to try and cover it up with my hand. How much force am I going to have to hold back? It's 14.7. Pound is so a force, Ruhif. It's what he is, a unit of money. So I have 14.7 pounds per square inch on one side, 0 pounds per square inch on the other side, and I have a 1 square inch hole. I have to hold up 14.7 pounds.
Right.
I can handle it. Okay. I'm okay with that.
Gotcha. So the torus space is only 14.7 pounds per square inch.
No, the standard atmosphere that we live, 14.7, we say, that's just the standard atmosphere. That's where we live. Space is effectively 0. It's a very small number. It's not a very large torr. It's a very small torr. Right? When you hear the number, people will often say like 10 to the minus 7 or 10 to the minus 17 or something like that. Right? They're quoting numbers for different places in the universe. 10 to the minus something means how many zeros in front of the number. So we're not talking about tremendous forces. We're talking about teeny, tiny, little, teeny, weeny things. Things so small that when you subtract it from our normal 14 pounds, it's 0. It's fine. Just call it 0.
That makes sense. That's fair enough. So, okay, so then this is if I may, I'd like to offer a thought experiment, um,
Go.
kind of like the reverse of what you have laid out here, just to kind of see where we get to it with that. If we can agree on how this works, and then maybe help with the block that I'm having here, to kind of help you see what I'm seeing. So it's true that when you have the pressure, when you have an area of low pressure, an area of high pressure, generally they will attempt to equalize each other out. Now, sometimes, well, generally you'll get a gradient inside containers. But basically, what I'm getting at is when you have the equalization happening, let's say you have area of, I mean, this is a better question. I'm sorry, I'm kind of all over the place. It's late. A better question would be, at what point do you actually start to would you actually start to notice a transfer of pressure?
At what point would you notice a transfer of pressure? Depending on the precision of your instruments, I suppose. Um, when would we notice it is when we feel a wind, when we feel a breeze.
So the reason why I asked that is because, again, if you have the area of low pressure up high, right, and then you have the
Yeah.
area of, and of course, assuming there's area to escape to, right, because that's trying to equalize.
Yeah.
And then you have the area denser down below. The denser area flows to the less dense area, at whatever that rate is, until it equalizes to the outside gradient of whatever that room is. So if you have um, I'd say a gradient that's infinitesimally small, right? Infinitesimally small, and
Yep.
the room is huge. Let's just say the size of a auditorium,
Okay.
and you have a thimble size gradient, right?
Thimble size gradient.
Like, let's say you have a thimble,
Okay.
right? I know this is a hypothetical because I
We have
don't
a
even know
we have a
gas.
thimble inside an auditorium.
Yeah, you have a
Okay.
thimble inside an auditorium. The auditorium is basically vacuumed out to have a very, very low um, pressure gradient,
Uh-huh.
and then the thimble has a comparatively high density pressure gradient inside the thimble.
Uh-huh.
You remove the
Okay.
thimble,
Move the top from the thimble, maybe.
sure, create an
Okay.
opening,
Uh-huh. Uh-huh.
explain, um, I guess, explain how that kind of situation. Because I'm comparing that to the Earth, to the vacuum of space, right? Because space is very, very huge. The Earth is very, very small. There's a small amount of gas on Earth compared to everything that there is out in the universe, the vast low pressure for the gas to escape to. So, in this much smaller, not even quite to scale example of the thimble with the auditorium, I'm curious to see how that example would play out.
Yeah, let's take a look at this. Um, Middlewell found this for me. Um, I've seen it before, but I was having trouble finding it. Here's, I think, your example. This box here, it represents a closed container, and it is evacuated outside the box. And so we just do this. We squeeze some air into our little simulation. Okay, and so we see, first of all, the first thing we're supposed to learn from this is why gases distribute their pressure throughout. They fill the vacuum of space because these gas molecules have momentum, right? And so they're going to just go and do their thing until they bump into something. And they splatter all over the place and fill the area, right? We're cool with this. Let's turn on gravity now. Here's gravity. Let's crank up some gravity and see what happens. Now we get our pressure gradient. You can kind of see it happening in the simulation. The molecules are being bunched up at the bottom. Let's open the lid and expose it to the vacuum of space, or vacuum of the volume. Now, some of the molecules are being ejected, right? They're getting sucked into the vacuum. Note, they're not getting sucked into anything. They're just bouncing out of their container, right? I think that's a major misconception a lot of people have. A lot of people think that the vacuum pulls It doesn't. It's just, it doesn't stop the molecules when the molecules get there, right? There's no lid. The walls are stopping those molecules, but the lid, no lid, they go through. But as you can see, the air is not actually rushing out. The high energy molecules they have enough energy to make it out of the top. And they go off and travel around into the auditorium. But the cooler molecules, the low energy molecules, they get stuck in that little container and they cannot get out. So what do you think?
Yeah, I'm just trying to wrap my head around it. It's I haven't really thought about pressure gradients and pressure differentials in this way. Normally, I think of it kind of like how you see water and things, like it's fluid dynamics, but just when it's air, it's a lot less dense fluid, right?
Right.
Um, so, I mean, I guess I could accept this as a, a example or whatever the heck you want to call it. Like, it's not a real world example, but it is a
It's a sim. It's a simulation.
right simulation.
It's a simulation of what science is trying to tell us. Right. Again, to reemphasize, you don't have to believe that this is true. But the question is, what does science say the explanation is? This is what science says the explanation is. That the gas molecules have momentum, because duh, and they also have weight, which I think we've agreed to. So if you take those two concepts together, momentum and weight, that's the deal. And there is a height of a wall where you don't have enough momentum to get over that wall, right? And how high is that wall? The question would become, well, how much momentum do you have? Like when I was talking to Alan some time ago about this, I gave the example of, just throw a baseball. I can throw a baseball over the back fence. That's no problem. The back fence will not contain my baseball. I can throw a baseball over a tree. It's harder, but I can get it over there. I cannot throw a baseball over a mountain. The mountain is just too tall a barrier for my weak arm to overcome. And that's the same deal with air. Lifting air requires energy. It takes energy to lift air up because it has weight. Lifting something requires energy. So if you wanted these last molecules that are in here to get out of there, you want them to get out of that container, you're going to have to give them some energy. They don't have enough. That makes sense?
I suppose. I mean, I'm kind of with you in the I don't have to completely agree with the explanation, but I can see where you're coming from. So that's all
Yeah, that's really all I'm looking for, is to agree to that science does say this is how it works. That's consistent with what science says. So a lot of times you will hear, the flat Earth folks will say that the science is not consistent. The science is contradictory. You'll hear all the time, well, that violates the second law of thermodynamics. You hear that all the time, but that's not true. The truth is that right there is a simulation of the laws of thermodynamics. And it says a container can, with an open top, can hold gas molecules.
I definitely appreciate the explanation. And one thing that's funny is that I don't really, argue with you too much on the gravity thing because we've already come to the agreement that we're just talking about the downward acceleration. Actually, it's kind of a good segue into the next thing that I wanted to talk about, which is um, how can we get to how can we isolate the variable for gravity to ascertain that that is in fact the bending of space time and not just electrostatic um, forces and things of that nature.
Well, Okay, so is that the question? Because that was well under 2 minutes. I don't even have to time that. How do
Yeah.
we isolate gravity away from electrostatic forces?
Right. And
Okay.
I'm talking not the obviously not the thing that you can Faraday cage away, the, obvious electric forces, but um, I'm talking about the forces between the I'm trying to think of the word for it. Sorry, it's been a really long day. The, electrostatic forces between the things in the atoms. Sorry,
Okay.
I butchered that.
Um, before I actually answer that question, I'd like to take your mind back a little bit. My thrust really is logic, just critical thinking and simple logic. That's why I really liked that thought experiment that we did earlier, which the point of it was not to tell you what science says, but to ascertain what your own logical thinking is telling you, and to realize that, see, Riff, to realize that if you follow your own logical reasoning, you're forced to admit we do not need a container. And yet, that isn't the conclusion that you drew, right? That's what I want to highlight, is that just the basic logic says a gradient, the existence of a gradient verifies we do not need a container. And if I follow the logic, that's what it says. And yet that isn't where you went. So let's do the same thing with your electrostatic gravity. If all mass is attracted to and electrostatically attracted to other types of mass, that should create a gravitational vector, right? That's your thinking. And if we have a gravitational vector where objects are attracted to one another, all objects will be pulled into a spherical shape. And we have Newtonian gravity driven by electrostatic force. You've logicked yourself right back where you started. And what do you have to say about that?
I'm actually really glad that you brought that point up, because that's actually something that I have considered myself. But the thing that I kind of got away from, and that I had to get away from, is this whole idea, this whole antecedent that just because that the objects are attracted to each other, that means that they're going to be all attracted into spheres. Now, that may work if we are dealing with in fact, an infinite space with, floating, space rocks. I see that as a possibility. However, if we are dealing with the alternative worldview where we're at the basement of the universe, then it would also make more sense that the majority of the density, the majority of the mass is going to be beneath us. So that's actually why the vector is pulling us down. Um, Pretty much that's
Yeah. Um, but I mean, the beauty of the logical hole you just stepped into is who cares? Uh, and right, the whole argument of gravity isn't right, whatever argument is completely invalidated by the electrostatic gravity argument. It right. What were you trying to prove by establishing that gravity isn't gravity, that it's actually electrostatic? Were you trying to prove that the Earth could be flat because of that? Because it doesn't get you there.
I love it, by the way. I appreciate your questioning. It's awesome. So, where I feel like we get at is that people are trying to say that the exact same force that is holding us to the ground here on Earth is the same force that is causing the lights to be circular in the sky, and then causing those lights to then circle, in particular patterns around us. Or it's actually not them circling around us so much as it is we circling with them around another body, then circling another body that's circling another massive body.
Right, right. But does this electromagnetic or electrostatic whatever idea get you out of that? Or did we just get back to why does Mars orbit the sun? Oh, because it's attracted electrostatically to it. It's an inverse square law force, right? Does Coulomb's law still apply? I'm kind of curious about that. And your idea of whatever this electrostatic thing is, we still have Coulomb's law?
What is so I'm actually not familiar. What is Coulomb's?
Okay, it just says that the amount of force is proportional to the product of the charges and inversely proportional to the square of the distance between them. It says basically, as the two charged particles get closer, they're pulled harder, and they're farther away, they're pulled less.
Gotcha. Honestly, I don't know enough about it. That's part of the reason why I'm here. I'm not an expert on the science or the mathematics.
Okay.
But I was wondering, again, my question was the isolation of the gravity variable. Regardless of how you want to interpret, just swapping it out and you want to keep everything exactly the same, that's, fine with me. But I assume that there's a reason that science has come up with the idea that there's this thing that's bending space-time. And I'm curious.
Absolutely. Okay, so let me give you the 2-minute answer then. How do we isolate it? Just with the understanding that logically, this does not get you a flat Earth, right? Because it is mathematically equivalent to Newtonian gravity, right? Your electrostatic gravity solution is mathematically equivalent to Newtonian gravity. So anything that works under Newton is going to work exactly the same under your electrostatic idea, which I think is just really telling, right? There's a big, deep message behind that. But how do we know it isn't that? First of all, the Coulomb's law. Coulomb's law says that the amount of force is proportional to the charge on the objects. When you rub a balloon on your head, you exchange charge between your hair and the balloon. We all know this, right? So you rub a balloon on your head, you give an electrostatic charge to the balloon and a different one from your hair. And that force, or that charge, is enough to stick a balloon to the wall and to defeat gravity by sticking a balloon to the wall, right? But it does not change the weight of the balloon. So whatever is causing the weight of the balloon, when you put a balloon on a scale and we read a number, it is not related to the electrical charge on the balloon. And it's that simple to demonstrate that those are not related.
I like it. It's simple. It's easy to understand.
Cool.
I mean, it's something that I'd obviously like to try myself, but yeah, if that all checks out,
I think that would be really cool. Rub a balloon on, well, first weigh a balloon, then rub it on your head, and stick it to the ceiling, make sure that it worked, and then weigh it again and see if it weighs anything different. I mean, obviously, it can't weigh much different because we were still amazed that it stuck to the ceiling, right? It's not like it floated up to the ceiling, right? So yeah, one of those things where we kind of already know this.
Well, it didn't float up to the ceiling because it was obviously
because it still has its weight. It still has its weight, right? Even after you rubbed it on your head. But so if weight, the phenomenon of weight, was related to electrostatic charge, changing the electrostatic charge should change the weight, and it does not.
Wouldn't it also, and I'm throwing this out as a question, obviously. I didn't come prepared tonight for the flat Earth debate, but I appreciate you firing away.
Okay.
When it comes to the static force not having anything to do with the weight, you say that it wouldn't change, but then you also said that it might not change much. Wouldn't it also possibly be true that maybe we're just not adding enough charge, that it's a proportional effect and we have much more charge with the Earth versus the static charge that you generate by rubbing the balloon on your head?
Yeah, absolutely. I would invite you to check the numbers, right? And you could design entire experiments out of this. Shouldn't be too expensive to do that kind of thing. You hear sometimes that there's this tremendous voltage difference in the atmosphere from the ground to the atmosphere, and this is the source of it. Sure, but a Van de Graaff machine, generates tens of thousands of volts all by itself. So there's a huge voltage difference available to you just by rubbing a balloon on your head. It's not a small amount, it's a huge amount. So yeah, that's what science says. I would invite you to investigate that a little bit. See what is Coulomb's law. What does that say? I would also really invite you to investigate what is incoherent static charge, because that's not even a thing. That doesn't even exist. It's just, if you want to know the truth, it is, we do not want gravity to be real. We see that Coulomb's law is very similar to Newton's law. What if Coulomb's law is Newton's law? Therefore, gravity is caused by electrostatic. Bang, look at that. That's beautiful. We proved we're right and science is wrong. And then someone does the balloon experiment and shows, no, you're wrong. And then we say, yeah, but this isn't electric charge. This is incoherent electric charge. And then science just like, okay, I don't know what that is, because there's no such thing. I mean, not in science, right?
Are you familiar with, I'm sure you are, you're familiar with the experiment that Whitsitt shows where they're using a Van de Graaff generator to make a balloon rise and fall, and then they also take it and they use it for the tinfoil. So what would
Yeah.
science say about what's going on there?
Okay, well, Coulomb's law gives us an exact amount of force that is generated by a charge difference. So if you charge something up and you create a voltage difference, you can make something hover. You can make it counter its own weight. You have not eliminated its weight. You have just created a counter force that holds up against its weight. Right? I mean, that makes sense. That's what that would say. There's also a possibility, I haven't seen whether he uses this, but there's also, ionic thrust, which is pretty cool, but I don't know if they've looked into that. You could take it further, right? If you really charge up, you create a large amount of charge on something, and you put a sharp point on it, the charges will flow to that point and just be ejected. And the buildup of charge on the point will cause the air around it to flow, and you'll get like a little jet. You can make a little electric jet. It's pretty cool.
Gotcha. So again, just to summarize, make sure I understood properly and correctly, you can isolate the variable for gravity, not by isolating gravity itself, but by at least isolating the static force away from it, or at least by showing that it has not enough of a relationship to, I guess, warrant the force of gravity or the force of the weight, whatever you want to call it. Doesn't really matter.
Yeah. You can certainly isolate electrostatic charge. You can put a measured amount of electrostatic charge on an object and measure the effect on its weight, and do a graph, like make a graph of charge versus weight. And if weight is caused by charge, you expect a linear relationship there, or some kind of relationship. I mean, I guess it could be something else, right? But you expect some kind of relationship between charge and weight, and you will not find that. You'll find that you can do it if you arrange an opposing charge near it to float the thing.
Gotcha. Yeah, that's so far so good. Again, I'm not saying that I agree with all the explanations, but like we said, I appreciate you being very clear cut and helping me wrap my head around some of this stuff. So, I guess the last thing that I wanted to bring up would be the whole relativity thing. I just want to make sure that I'm crystal clear on that. Make sure there's no misconceptions on what I think I understand about that. I'll just ask
Okay.
point blank: is it true that basically the effect of relativity is that from the frame of reference of Earth, you could never prove that it's orbiting?
I'm going to say no on that one. I believe I've seen a lot of that going around. I think Whitsitt likes to bring this one up. I tried to look into that and see what the heck they were talking about. There's two potential explanations for what Einstein was saying in the quote that is often bandied about. Unfortunately, Einstein's not here to ask, really. That's what you would do. If you want to know, Einstein, what are you talking about? We should ask Einstein, but he's not with us anymore. So there was a letter that he wrote to Ernst Mach, I guess, that said something to the effect of no optical experiment can determine the motion of the Earth, or something like that. Is that?
That was you're close enough to one of the quotes, but there was another one where he says that I've already mentioned in regards to the terrestrial experiments of the terrestrial kind, that all experiments of this nature have led to a no result.
Okay. Well, the Einstein's basic principle was that, Einstein's basic principle that he used for general relativity was the equivalence principle. Einstein realized that gravity and acceleration behave exactly the same. You may have noticed that before. You spin around on the wheelie ride. What do they call those at the circus? Gravitron, right? And you get stuck to the wall like it's got gravity.
Isn't that centrifugal force though?
Yeah. It's a centrifugal force. Like, as an engineer, I'm happy to call that centrifugal force and say that's a force just like gravity is a force. In fact, we'll come back to that. Often you'll hear physicists say centrifugal force is not a real force. You're feeling centripetal force. And you're like, what is that? The wall is pushing you into a curved path, right? The wall of the gravitron is forcing you to go in a curved path, right? I think we're on board with that.
Sure.
That forcing you into a curved path means it's accelerating you. And it feels like gravity feels. Gravity feels like the floor is accelerating me upwards. That's what it feels like. And then, so Einstein says to himself, what if I was closed in an elevator and I have no windows, I have no way to know what's going on, and I'm just standing there? How do I know whether the elevator is pushing me up or gravity is pulling me down? And when he realized that, he said, that's the key. The key is that the gravity we feel is an acceleration, that they are equivalent, they're the same. And then he goes and he says, can I work out a mathematics in which I can express that gravity and acceleration are the same thing? And that's what he went and did. So when he said there's no terrestrial experiment that can prove motion, I think possibly he's really just talking about special relativity, which is just really Galilean relativity. It's just when you're driving a car and you look out the window, you say, oh, look at those trees flying by at 50 miles an hour. That those trees are flying by. Look at those trees. Those are fast trees, because I'm just still, right? And a bumblebee gets in the car and it flies next to you. And it's like, oh, look at this bee. This bee, he's hovering in midair. He's not moving. He's not moving at 50 miles an hour. He's just hovering. The trees are flying by at 50 miles an hour, right? And so Einstein, I think the basis is just Einstein saying, that's the thing. You can't tell whether you're moving or they're moving. There's just no way to tell. And then we can go further to say, are we accelerating or are we in some kind of gravity well? Can't tell the difference there either. Is that? I mean, that's it. That's really it.
Gotcha. So, part of the explanations that I've heard on why it can't be proven, the Earth's motion, due to relativity, of course, is that part of that is the length contraction. So in the Michelson-Morley experiment, It's noted that one of the possibilities is that the measuring apparatus literally shrunk in the direction of the acceleration. So
Yep.
so it's so that I mean, that's why, and I'm trying to get clarification on this point. I'm trying to figure out how I can phrase this into a question for you. Um, but basically, that's one of the reasons why it's believed that we can't prove from the reference frame of the Earth's actual motion, right? Because when you attempt to measure it, the not only will you not get a different result with the light, but also the measuring apparatuses are contracting as well. So there's no terrestrial experiment that can demonstrate it. Am I correct in that
And
logic?
I'd say you're overcomplicating it. Really, that one we can explain just fine with Galileo. I mean, Galileo before Newton, like before Einstein, is hundreds of years ago. Um, Galileo realized that the concept of velocity, like how fast are you moving, it only has meaning in comparison to something else. You can't say, how fast am I going? I'm going 50 miles an hour. We understand that means relative to the ground. Like I'm going 50 miles an hour faster than the ground. Okay, fine. Close the windows, right? Do you ever been like on one of those motion simulator rides, like Star Tours or something?
Something like that, yeah.
Sure. Okay, you're riding the ride. It feels like you're moving. They trick you into believing I'm moving. You can get into it, right? And the way that works is the same deal, which is you can't tell absolute motion, right? If you're riding on one of those rides and you drop your pencil, it drops straight down. It doesn't go zooming back. You can ride on an airplane. Ride on an airplane. If you wake up, you're in an action movie, right? Somebody drugs you. The bad guys drug you and they drag you off onto the private jet. You wake up, oh, disoriented. Where am I? Where am I? You don't know you're moving. You're in an airplane flying 500 miles an hour. You can't feel it. You can't measure it with anything on board. You drop something, it's going to go straight down. You look out the window and now you realize I'm on an airplane, right? That's what Einstein was saying. You can't look out at space and say, oh, look, the stars are flying by. Well, wait, does that mean we're moving or are they moving? Galileo taught us that it's a meaningless question. You're moving relative to something, and there is no other question that has a reasonable answer. Does that make sense?
Yeah, I can kind of get on board with that. So we pretty much are on the same page in agreement that from the reference frame of Earth, at least, and I'm not even going to invoke conspiracy or anything. We don't even have to talk about NASA. Um,
Okay.
but at least from the reference frame of the Earth, according to Einstein, according to relativity, it pretty much is a correct statement to say that it is unprovable which way to to say that it is right, that either we're moving or that the sky itself is moving.
Yeah, pretty much. There is a caveat to that, though, which is rotation. Um, and this is where things do get a bit sticky. And that is if you get on the gravitron, you get smashed up against the wall. So you can be assured when you're on the gravitron that there's a force there. You're feeling a force. It's an evident force. So the gravitron is not stationary. Either that gravitron is accelerating you, or there's a giant gravity well on the other side of that gravitron that you can't see, right? So we can use measurements of acceleration or of rotation to say definitively, for example, that the Earth is going around the sun is not going around the Earth. So we can actually we can be assured of that.
Okay, so again, just to make sure that I understand crystal clear, you're saying the measurement of the force of the rotation is how we can tell that we're moving around the sun?
Well, actually, it goes even further. Since rotation is non-inertial, we can literally measure the rotation directly. We can just say, give me a gyro compass, give me a fiber optic gyro, set it on the desk, turn it on, measure the absolute rotation rate that it is experiencing. That is not relative. If I put a speedometer on my desk, it's just going to read 0. It's not going to be able to read the speed of the Earth zooming through the universe. But if I put a gyro on my desk, it'll read the absolute rotation rate that I'm experiencing.
Okay, and I hope this next question doesn't seem, like I'm trying to be an ass or anything, but was this technology like not around during Einstein's day, or is this something that's new? Or
No, it was known. It was absolutely known. My interpretation is, here's the thing: is Einstein's not here to ask. So the best we can do is try to interpret his words. My interpretation of his words were that he was talking about what I would call translational motion or linear motion, moving in a straight line. Like how fast is the sun zooming through the universe was a question we literally cannot answer. It cannot be answered, according to Einstein. But he was not talking about spinning. Spinning we can literally measure, and he knew it. So I don't think he would have said that we can never measure spin. That said, I have read some things that indicate that Mach himself, the man he was talking to, was arguing that it would be conceivable that there's a force driven from the universe itself spinning that is somehow influencing the spin that we measure. And it's entirely possible that, you won't find any scientists today agreeing to that. You'll find some, but the mainstream definitely does not agree with that. But I could imagine that maybe Einstein was acknowledging Mach and saying, well, technically I can't disprove that, right? Maybe there's the universe is rotating around us, and the rotation of the universe is dragging our measurement devices and dragging our, everything with it. And technically I can't disprove that. It's just, ludicrous. Right.
Well, everybody's entitled to their opinion, right?
Yeah.
It's like the best example that I've heard of how that's possible is like translation of motion. You have a bathtub, you have your hand, you wave your hand above the bathtub, and even though you're not touching the water, the wind that you create from your hand is enough to move the water. So it's just a translation of motion or a translation of force through that, and to which
Okay.
you probably then have another antecedent. Well, then there'd have to be a median, and that's where the ether, of course, would come in. But that's neither here nor there. With my next question, you actually reminded me. It's in regards to the laser gyroscope. This is more for personal curiosity than anything, but the ring laser gyroscope, is that basically a mini Michelson-Morley device? Like what is that? How does that work?
It's a mini Michelson-Gale device. The Michelson-Morley experiment, it bounced 2 lasers at right angles to try to see, is there a different speed this way than there is this way? And actually, it's a mind blower. But what they found was no, the speeds that they measured going this way and going this way were identical speeds, no matter which way they pointed it, at least within the margin of error at the time. And modern devices have much smaller margin of error, so we can say confidently it's the same speed. Okay, so from that, they decided that the ether, if there is this ether, it must be moving at the exact same speed as the Earth. because there's no relative difference based on direction. So that's what Michelson actually thought. Michelson wasn't a big fan of Einstein. He thought that the ether must be drug by the Earth so that it's moving at the same speed as the Earth. But then they did a follow-up experiment called Michelson-Gale. So different, and there was a third guy on that one. I forgot his name, starts with a P, but usually just called Michelson-Gale. And that they sent the laser in a circle, or well, a square. They sent it in a square, bang, 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 bang. 2 lasers, one clockwise, one counterclockwise, around in a square. And with that, they were able to determine that there is a difference in the speed of the lasers going clockwise versus counterclockwise. That despite the fact that the speed going this way is the same as the speed going this way, the speed is different going this way than it is going this way. And at that point, Michelson was just stumped. He was just flat stumped because you can't resolve those two things. He was imagining that they were like you're in a boat in a river, trying to measure the speed of the boat by dropping a buoy, right? If your boat is flowing at the same speed as the river, the buoy just sits there. And that's what he thought he was looking at. But then he measured the speed of it going around and found going around one way is different from going around another way. So it's like you're in a whirlpool. You're sitting in a whirlpool. But if you're sitting in a whirlpool, then the flow's got to be going one way on one side and the other way on the other side because it's going in a circle. But it isn't. The buoy is sitting still when you just drop the buoy. But if you put the buoy in a circle, it shows that there's a whirlpool. And yeah, Michelson was just plain stumped on that one. And if you're a flat earther or a geocentrist, I got to say, I think you're going to be stumped as well. There's no explanation using ether for that. The only explanation I can offer you is that ether does not work like that. Ether doesn't work like water in a river. It does something different.
Gotcha. What would be the follow-up question? What would be the globe Earth explanation for that discrepancy in the motions?
Well, the usual answer is you'll hear people say there is no ether, no such thing as ether. I have an oddball opinion on that. I would say ether is the medium that light travels through. That's the definition of ether. Ether was imagined to have properties like a river. We know that it does not have properties like a river. The medium we now understand is called the electromagnetic field. The electromagnetic field is the medium of light. And so therefore, the electromagnetic field is ether. And so if you insist there must be an ether, I will tell you, well, that's called the electromagnetic field in modern language. We call that the electromagnetic field. And special relativity, not even general, just regular special relativity, tells us that the speed of light, because of the quirks of how the electromagnetic field works, the speed of light is always a constant in any direction, no matter what the speed of the observer. However, if you go in a circle, that's non-inertial. You are accelerating, right, to go around in a circle. And so you can get a difference now between one way or another way, going with or against the rotation. And that's exactly what we measure.
Interesting. Well, yeah, this stuff I haven't heard at all before. So I've heard of the Michelson-Gale, Michelson-Morley experiment, but I haven't heard about that other little motion there. So that's going to be pretty fun to look into, broaden my research. It's been an excellent learning experience so far. So I definitely appreciate you offering that up. I'm trying to think of, I did have a few more questions, but when you're explaining, sometimes I forget them. So You'll
That
have to.
happens. That happens. I'm so mesmerizing.
I'm I'm an avid consumer of medical THC, so my memory is not the greatest all the time. But
I can dig that. Okay. I don't partake, but I can dig it.
I had another good question, so I don't want to let it go.
Okay.
Uh, man, give me 1 second.
Also, any questions from folks in the audience? We can have you guys do some questions too.
Yeah, absolutely. Fire away. If you guys don't think I'm doing it justice, then feel free to see if you could do better. But
Yep. And I'll give you a minute to think, and maybe I'll ask you a question.
yeah, fire away.
Something I'm interested in these days is I've heard you call yourself like a true earther.
Right.
True. What's truth? What is that?
It's whatever that's closest to objective reality, as in we can both agree that we're online right now and that we're streaming. That's objective. There's really no debate on that. So I use the term true earth because it's a title that tries to attract people from every audience. And it actually does a pretty good job of doing that. When I started doing this on TikTok, I got not only flat earthers, globe earthers, but I also got a lot of concave earthers and people who just have completely different ideas about the way that all this can work. And it kind of takes me back to a quote that I've heard tossed around in the community a lot from George Ellis, and that there's a range of models that could explain the observations. And when you think about that, it's like, man, you can't just be talking like one or two. When I think of a range of something, I mean, you can't put an exact number to it, but it's definitely more than a couple. So, I mean, flat, globe, concave, those are just 3, particular models of the Earth. I like True Earth because it tries to avoid the one label, attracts people from, every walk, and then that way the conversation can actually flourish and, stay dynamic. The worst thing
I
for
dig that. That's good.
the worst thing for any contentious topic, in my opinion, would be to have an echo chamber, so I try to avoid that.
I respect that a lot. And as I was telling you before we started the show, I went and watched some of your content, and you're true to that. You have people from both sides come on, and I've seen you even take like I know you have a particular side, and I think everyone's aware what that is. But you seem to be willing to sort of entertain almost the other idea, um, which is pretty special. I really like that.
Oh, yeah, for sure, and again, there's nothing wrong with having an open mind and taking in information. And just because some information may contradict, with what your worldview is currently, it doesn't mean that it is always going to, or it doesn't even necessarily mean that the information is completely objective. A lot of times when you scrutinize things, you'll find out that it's a little bit more complicated than what people are led to believe. The gravity equation is a big example of that. A lot of people, when they see that letter G, they think of that whole entire mass attracting mass equation that they have to work out, when in reality, it really is just that simple, acceleration. But yeah, I definitely appreciate you checking it out, and, I appreciate everybody who tunes in. That's the whole point of the of the platform, is to have people tune in, check out the conversation, formulate their own ideas and opinions. And hey, if that happens to be with the mainstream, then whatever, more power to you. But we do get a lot of people that, especially as of lately, with all the other stuff that's happened. I'm not even going to get into it. More and more people have started to question the mainstream narrative of just about everything, and the truth doesn't fear any scrutiny, regardless. So if the mainstream is true, then they should be like, bring it on, just like you are, Matt. It's really, I appreciate your channel and the way that you do things, because you have us on, you answer our questions point blank. You don't run from the contentious issues when it comes to, hey, it
Not
is,
these.
yeah. Hey, there is another possibility for, the what's going on with the ring laser, but um,
Do you have an alternate explanation for the ring laser?
no, just the translation of motion. Same thing that
Translation of motion.
basically the same thing that you were saying with Mach. I mean, there's no way to.
Yeah, he's like, there's some kind of mystical force in the universe that we can neither confirm nor deny that is causing this.
But you can call anything mystical if you don't have the exact measurements for it, right? I'm sure. If we assume that the mainstream is 100% true, then you could easily call gravity this mystical force. So.
Gravity is pretty mystical, no question. It's just that we can measure it, right? And we do. So we know that it's real. What causes it exactly? Still up for some debate. The headline right now is gravity is Einstein's GR, is the best explanation for gravity we have. But then you can ask why, right? You can say, but why? And that's the nature of all of science. Right? Literally anything. You just ask why, and you'll eventually hit the limit of human knowledge. Right? You say, oh, I dropped the pencil and it fell. Why? Oh, gravity. Why? All things are attracted towards the ground. Why? Well, because all mass is attracted to all other mass, according to this equation. Why? Oh, well, because the mass is a concentrated form of energy, and energy bends the space-time metric, and all objects try to maintain a straight line in space-time. And why? And then you're like, I don't know. I don't know why matter should bend space-time. And I guess why objects want to maintain a straight line, you could probably say principle of least action would probably be your bet there. But then you'd still say why. You can always just keep saying why until you hit the limit of what people know. And when you hit that limit, that's where graduate students live. Right? That's what graduate students do. They try to answer the whys that we don't have.
Yeah, absolutely. And I think that's, a lot of people complain about speculation and stuff. It's like, oh, well, there's too much speculation in the scientific community. And, that may be true. There may be some truth to what Tesla was saying about the, scientists of his day drifting from equation to equation, building the models. But even with that being the case, it is true that at some level you have to start with some level of speculation in order to move forward. So, I mean, if we don't, you start as an infant, I mean, you got to speculate before you can learn. So that's just an honest and obvious fact. So that doesn't need to be a point of contention too much. What we do like though is we do like to try to get a hold of the terrestrial experiments, the things that when we don't have to rely on an authority figure to tell us that this is how it works, when it's something that, um, okay, so great example would be, and this is something that I've heard mentioned before as well, and it's kind of getting back into the gravity topic with the um, Cavendish experiment.
Okay.
So with the Cavendish experiment, Cavendish was noted to have taken all kinds of painstaking precautions with his testing. Like he had it do it in a shed. He observed it through I think either binoculars or a telescope or something. He was looking at it from a distance, manipulating it with string.
Yeah.
Um, there was all kinds of variables that he was trying to isolate, and at the end of it, I mean, again, I'm a little unfamiliar, but wasn't it true that he said something along the lines of it was impossible to isolate all the different things that can throw it off, like the actual shed itself has gravity, and um, the string has like everything in the entire experiment has gravity. So
Mm-hmm.
how is he able to, how are we isolating it to just the balls to get basically how are we isolating the variable to
Right.
get the cause effect relationship?
Right. Okay. That's a good question. I don't know if he ever was quoted saying anything like that, but how do we isolate? Um, the way you isolate these things is with control. You say we're going to put it like this, and then we're going to change one thing, and look for a reaction. So have we changed other things? If we have accidentally changed other things, those would be a confounding variable we would want to try to get rid of. So you try to just change the one thing and then draw a relationship between that. And so the one thing he was changing was the placement of the exterior masses. So just by moving the exterior masses, do the interior masses react, and in what way do they react? And so if you're saying, yeah, the strings that it's hanging for have a gravity, yes, they do, but that hasn't changed. They were there before, and they're still there now. The walls of the device have gravity, and that hasn't changed. They haven't moved. So whatever influence they have was there before. So when we change the one thing, the position of the large masses, we're looking for a reaction. And he got one.
So my follow-up would be, when it comes to the Cavendish-like experiments, has one been done where you are actually able to, let's say, decrease the weight of an object by holding an object of high mass above another object? So that in effect, the gravity from the object that's placed higher pulls, in a sense, the object that you're weighing?
I'm fairly sure that some university somewhere has done a real one. There's a video of one floating around the internet that I do not trust. I don't think that's reliable. So if you see the video, the guy just puts a lead ball underneath a weight and the tick goes up. Back of the envelope calculations suggest that should not have worked. And so I think that one's bogus. But I think they have done this experiment in, you're going to need a serious setup to do it, though. So we're talking at least university level, science setup. It's not a backyard experiment to do that one.
Gotcha. I had another good question. I'm starting to think of them again. So
let me add, though, there is a gravimeter. There's a device you can buy. They're fairly expensive, but there's professionals who use them for a living, and that's exactly what it is. It measures the drop rate inside an evacuated chamber inside it, and what they do with it is they move it around the surface of the earth, looking for dense locations underneath them, measuring changes in gravity in different locations. So you would probably argue, well, maybe it's something else causing that, as opposed to a change of density below them. And maybe it is, but they use it to drill for minerals, right? That's the purpose of it. They're looking for valuable minerals under the earth. And it's big business that they do that. So
sure. Can I also ask, this is a question I just thought of. It's another relation into gravity, is when it comes to calculating the gravity of objects or the weight of objects using the mass attracting mass formula. Is there any part of the formula that actually does dictate that everything does condense into spheres, or is that just a thought experiment, or a theory that it's just thought of that would happen?
that's a good question. I think you're going to get different answers. Depends on who you ask. The equation does not literally say, and thus everything is a sphere. It just says that there's an attraction between objects that's radially symmetric. Radially symmetric, meaning the amount of force doesn't care what direction you're in. It cares what distance you are, according to that equation. Does that make sense? So like, it doesn't say moving, like if I have two objects, it doesn't say that this will create a force any more than this will, right? This is the same as this, according to the equation. So anything that is radially symmetric like that has the same behavior in all directions, will give you a spherical result, whether it's an attraction or a repulsion. A shock wave expands in a sphere, for example, right? A bubble creates a sphere. Same fallout comes from any equation that has that symmetry to it that's the same in all directions. You're kind of forced into spheres as a result.
Gotcha. All right. So I'm gonna go ahead and roll on to the next one, unless you have anything following up with the gravity.
No, go ahead.
Awesome, man. I really appreciate this. Super big shout out for the platform, man. All
I
right.
appreciate it. Yeah.
Yeah, absolutely. So, with that being said, the next one is gonna have to do with parallax. I know that you're more into like the science thing. I'm not sure if this would still be, part of your expertise or not, but when it comes to parallax, a lot of people, and at least I've heard the claim that the parallax is like big proof that of the motion of the Earth, through space. And
Mm-hmm.
there's a couple issues that I have with that, and I'm trying to again to phrase it into a question. It would be this: um, when it comes to parallax, what would the scientific explanation be for the occasional measurement of negative parallax?
Negative parallax. That's a new one to me. Negative parallax, as in there's presumably a star that you measure going backwards as we orbit the sun. I'm not aware of anything like that. Although Professor Parks is in the chat. So, Professor Parks, is there such a thing as negative parallax? I mean, in computer graphics, we definitely have negative parallax. I think what I would call negative parallax, which is we just are simulating something in the foreground.
I believe the answer that I've heard for it is that it's human error. It's assumed to be human error, and so you just
I
have
would
to.
absolutely say that. If anything has a parallax counter to the motion of the planet. Okay, yeah. Professor Parks, PhD, is an astronomer. So he says, observational error, the stars are at the limit of the technique. The error bars are huge and no one believes those results. So not human error, he says, instrument error. And I would concur with that. I'm not an astronomer, but I do optics, right? I teach CGI. I teach kids in college how to do computer graphics. And in order to do that, we have to understand how light works, and we have to simulate the real world. And so if something is moving in the wrong direction, that would be impossible, really, with a physical optical system. However, what Dr. Parks there is saying is that we have error bars in everything we do. We have, I mean, you're familiar, right? You get the idea. When you make a measurement, it's, I measured this thing, it's 3 millimeters long. Like, is it exactly 3 millimeters? Well, I mean, it could be 3.5, it's 3 millimeters. It's less hard to measure, right? So you say it's somewhere between 2.5 and 3.5 millimeters. And then you say, okay, I measured this other thing and it was 2 millimeters. You say, is it exactly 2 millimeters? Well, okay, it's between 1.5 and 2.5 millimeters. So you say, well, which one's bigger? Well, I'm pretty sure the 3 millimeter one is bigger, but within the tolerance of my error, they could be exactly the same. They could both be 2.5 millimeters for all I know. You get me?
Sure.
So if your measurement comes back and it says that the difference there was -1, you need to look at the error bars to say, is that a significant result? Is it like, no, it's absolutely -1? Or is it anywhere between -1 and +1, right? Or anywhere from -2 to +1. And if that's the case, then you could have a positive 1, right? I have never heard of a negative parallax before.
Yep. So supposedly what you're supposed to do is you're supposed to exit out and redo it, redo the measurement.
That's
So,
consistent with what Professor Parks is saying. Yeah.
so and I'll offer a little bit of my personal experience when I was in high school, and this is obviously this, in America anyway, this is something that's pretty common. I've heard this story quite a bit.
Mhm.
With regards to the science classes. And I know that we can probably take the position that, well, this isn't what science is supposed to be, but it is what it is for the public school system. When we're doing an experiment, and I'm trying to remember the name of the experiment, but the one that we were doing is we're basically taking a ruler and we stand it straight up, and then we have a bouncy ball and we're dropping it next to the ruler, and we're basically trying to make it bounce straight up and not go side to side so that we
Okay.
can measure the rate of the bounce.
Mhm.
And what we're supposed to do is we're supposed to take this formula and we're supposed to calculate the rate that it's expected to bounce. And then if when we do it, if it doesn't do that, we're literally told to scratch the results and try again until we get the expected result. And unfortunately, this is kind of something that happened. And with the bouncy ball, it's easy to see what all the different errors that can happen with that. And
Right.
any experiment, I'm sure, has its
That's
own
a.
error
I mean, if you were just holding that ball with your hand and dropped it, that's a sloppy experiment. Your error is going to be tremendous on that, right?
for sure. But I'm just
But you
kinda
were told, no, that's wrong. Do it again, right?
oh, for sure. But
Yeah.
basically the point that I'm making is, and that's not the only example, is that in pretty much any experiment that we're doing in school, if you don't get the expected result, you assume that it's an error, and then you do it again until you get the expected result. Is that I mean, that's fair.
Yeah. I've had a similar experience in school, although now that I've grown up and hey, Ruhif Spec. Now that I've grown up and I have a what I consider pretty healthy relationship with science education now, I kind of see it a little different. And let me tell you my story. It's just like your story. It was the pendulum experiment, where you have a pendulum and a stopwatch and you time the period of the pendulum. And the experiment was, how does the mass of the pendulum bob affect the period of the pendulum? And I came back with the fact that the heavier pendulums had they didn't swing as fast. I think I don't remember which one. I'm going to say they were slower. I'm going to say heavier pendulum is slower, and that was my finding. And just like what you're saying, the teacher told me, no, it isn't. You interpret what he told me was not do it again. He just told me you interpreted the data wrong. And at first, my reaction was, I think, similar to what you're feeling now and expressing now, which is that's bogus, right? Science is supposed to take this as real. But I grew up pretty privileged. I had a good science teacher. I've always had good science teachers. And he explained, he took the time to point at my numbers and say, according to your numbers, there is a trend that shows that the heavier plumb bob is slower. How much slower is it? It was, 3/100ths of a second slower. And he's like, okay, good. Do you really think your thumb is 3/100ths of a second accurate? And I was like, well, no. Right? When I stop the stopwatch, am I precise down to 3/100ths of a second? And I had to admit, no. So he's like, well, so if there is a relationship, the relationship is so tiny that you can't reliably measure it. That is what the correct interpretation should have been. And so, yeah, I would have wished that your science teacher had done that as well and said, not just said, go do it again, but maybe said, do it 10 times and look at the aggregate of data to get an idea of how much it varies from each experiment. And then tell me, like, what is the center line, and what's the relationship in there? What else can you learn? There's more to be learned here than just, we throw it out because we don't get what we expected.
Yeah, it was actually it was actually kind of like what you said, but also with we're gonna compile the data, but after we remove the fringe results. So, and that wasn't just one science teacher that said that, by the way. That was actually pretty much everyone that I did experiments with.
Yeah, it's actually a pretty normal practice to look at your data set, and when you have an outlier, that's the word for it, an outlier. You have one measurement that's just like goofy. A lot of times we'll just throw it out. We'll just say, okay, well, that one doesn't count. Somebody sneezed on the apparatus or something. That one's bogus. If you get a whole lot of data points that are just like right down the line, bang, 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 except this one, right? Is your takeaway going to be, there's two ways of looking at that. One way is somebody botched it. Let's just ignore that one. Or the other way of looking at it is, what happened here? Something really interesting happened here. I want to know more about that. And so, yeah, some scientists will focus on them instead of throwing them out. Maybe they'll focus in on it and try to discover something. Usually somebody sneezed on the apparatus, but honestly, a lot of times we just can't reproduce it, right? And that's the bottom line, is if you can't reproduce it, what more is there to learn here? And we kind of give up and say, I can't learn anything else from this oddball data point.
Gotcha. But of course, then we do have an issue if we do an experiment, we do get something that's uh, not expected, that's not a foreseeable error, and is something that we can generate repeatedly.
Yeah, absolutely. I'll give a little shout out to Bob Nodell, who is famous for his ring laser gyro that he got a hold of, or I guess it was a fiber optic gyro. And he verified the rotation of the Earth with it, and then, desperate to find anything else other than that, he took it up a mountain, and evidently he showed that the rotation was different at the top of the mountain than it was at the bottom of the mountain. And that's an unexpected data point. So that could be really exciting, to a scientist who's like, oh, look, I've stumbled onto something really great. Unfortunately, that was the end. That was the end of it. It never went anywhere. And so it just stands as an outlier, right? As an unexplained data point that, the rest of us cannot reproduce.
Or at least haven't attempted to reproduce it, to my knowledge. I mean, I know I personally haven't, but I don't have all the
Right.
money in the world to just go flying to the tops of mountains. But
Right. Yeah, I toyed with it a little bit, and I even had somebody willing to buy one. But I told him not to. And let me ask you a question. As a flat earther, I think you still consider yourself a flat earther, or a true earther. Would that mean anything to you if I bought a ring laser gyro and I took it to your house and I put it on your desk and I showed you 15 degrees per hour? Look at this. Would that change your opinion?
well, it's not really a point of contention for me. I actually agree that there's something causing a 15 degree per hour drift. The contention comes into, what exactly is causing that 15 degree per hour drift. So,
Okay. So yeah, it wouldn't mean anything to you. And frankly, I don't think it would change anyone's mind. The Globers would point to it and say, look, I told you it's 15 degrees per hour, just like we've said. And the flat earthers at this point would say, yeah, we heard that. We know. We don't care. So there's really no point in investing a lot of money in this. It's not going to change anyone's mind. That's the takeaway, right?
Well, I do actually think there is some value in exploring, Bob Nodell's, um, data point if we can, and I'm not sure exactly what that would mean, but if there is a different rate of rotation detected at different altitudes, I mean, that would kind of throw a monkey wrench in the idea that it's the Earth rotation causing that, wouldn't it?
If you could reliably do that, I would think, what I would do, what I want to do, what I wanted to do was say, hey, let's get that thing, and let's control for those variables that needs to be controlled for. Let's do it again. First, let's just reproduce it. Will it happen a second time? Will it happen if we go up the mountain and then back down the mountain? Is it related to pressure? Is it related to temperature? Let's try this thing. Just put it in a little, insulated, ice box
That's
with
good content right there.
with a fish tank heater. They put a fish tank heater in there and a thermometer, and see, does temperature affect the results of this thing? Put a bicycle pump and a pressure gauge. Does pressure affect anything? Or is it altitude? Or perhaps it was just drifting over time, right? So let's take it up the mountain. Let's take it back down the mountain and see if it reverses back the way it was. Those are all really interesting results.
Yeah,
So,
absolutely.
yeah, I would think that would be scientifically tremendous. And I often say, if you've got a result like that, that you can convince me is reproducible, I'll fund it because I want in on that Nobel Prize. Right? A lot of times, people like yourself are very dismissive of
I'm
academic science.
I'm skeptical.
Okay, but that's the thing about academic science. If I could make a true discovery that is not known, I'll be famous. I'll be famous and I'll be rich. I'm all over that. And we all are. So the thing is we know better. We've been down that road and we know it's not happening. So, you're going to have to go deeper than just a ring laser gyro. I took it up a mountain and proved that the Earth doesn't actually rotate.
Just out
It's
of
going to take
curiosity,
more than that.
has anybody else attempted to duplicate the results?
Not to my knowledge, nobody's ever actually tried to just literally duplicate that. But let me give you a clue. Every professional airline in the world has one of those on board. So they'd have noticed, if flying at 35,000 feet and their gyros don't go haywire, then why would 14,000 feet make a gyro go haywire? I mean,
Are they using the same, are they using a ring laser gyroscope that's detecting rotation? Or are they using just the one that's detecting the position above the center mass?
position above.
Or the one that just determines if they're tilting or not?
You mean they're the same? It doesn't matter. They're the same gyros. Yeah, the one Bob got a hold of, I'm sure, is designed for use in aircraft. That's its purpose in life. That's why they make them. There's very few other applications for these things other than aircraft and frankly missiles and rockets. I can't think of anybody else that needs that kind of precision on. Maybe submarines. Submarines, I guess, need them. Maybe. Precision gyros. Why do you need that? That's what it's for. So yeah, they make them, and they're kind of expensive. But if you're making a navigation system for an airline, you can afford it, right? And your multi-million-dollar aircraft, drop a couple of $1,000s on a gyro is no big deal. Yeah, your Cessna won't have one. right? Your Cessna will have maybe $1,000 gyro in it, a $500 gyro, and those aren't good enough to show that kind of precision.
Gotcha. Well, I think I'm out of questions at this point, at least for now. I would definitely be willing to do something like this again in the near future. I definitely appreciate you having me on, being cordial, answering the fullest my questions, at least as much as I can expect. And I appreciate one thing that I will also shout you out for is I appreciate that when you bring up a point that has another side to it, that you don't just say the globe part of the point and just completely leave off the other side. I can tell that you're a genuine person when it comes to having these conversations. So I definitely appreciate that.
Yeah, that's my thing, right? That's what this channel is about. It's about, let's don't have some kind of dumpster fire where we fight and make a spectacle. Let's try to get at the truth. Let's try to come to the concept of objective reality. Something you mentioned earlier, right? I mean, do we live in an objective reality? Right? Is there something that is truly real? And if we do, can't we figure out what that is? And how do we do that? So yeah, before we go in maybe the last 10 minutes or so, let me ask you, how do we determine what is objectively true versus something that maybe was pure speculation? Is there a way to determine the difference?
I think in a lot of aspects there is for a lot of scenarios. Now, can we test everything? I don't think so. I think that there are probably some things that we'll never know, as is the burden of the human experience. But I actually, unlike what you may believe or what some people may believe about flat earthers, I'm actually not a science contrarian. I do have my doubts in the mainstream scientific community in the way they interpret the data and the way that they choose to look and present data. But I actually do fully believe in the scientific method of isolating variables, creating controls. That way we can do the best of our ability to ascertain a cause and effect relationship. Um, I just think that with a lot of things, and again, some of this might be my own incredulity. I make no, from the very start of the show, I make no bones about the fact that I'm not an expert in any field. I definitely didn't go to college for, any scientific endeavor or anything like that. The best that I can say that I have is that I had an A in earth space science in high school. So you know, I
Yeah,
I think that I felt that I know a thing or two, and when I realize going through my journey just how much of it I haven't tested for myself, how much of it was actually just spoon-fed to me, and I did just take on faith. Um, Again, with everything else that's going on, I just decided that it was a good time to hit the old reset, start looking at everything with a fine-tooth comb, and that way we can actually ascertain what is true. I do still refer to myself as a flat earther because, and this is a position that a lot of us take, is that if you woke up tomorrow and you had no knowledge of science or anything at all, um, and nobody told you anything, you probably wouldn't come to the conclusion that you were on a spinning rock. You would most likely come to the conclusion that you live in a area where the sky rotates above you at a set rate per day, and that's what you would come to. So I do set with that as the base assumption, and then from there I do try to work to a point where I can ascertain proof of the curvature rate, proof of really any of the claims that mainstream science makes for the stuff that's unterrestrial.
what do you mean by proof? Can you define that for us? Because that seems to be a quite an issue in these circles. What does that mean to you?
So when it comes to when I'm talking about scientific sub issues, I'm specifically talking about scientific proof, as in evidence that has been gone through the scientific method to the fullest. I'm actually one of those that's kind of a stickler. I don't like skipping steps. I think that every step of it is pretty important. The observation, the hypothesis building, the data gathering, it's all, it's all a part of it. And if you end
We
up,
should have a follow up on that someday. I have a video on the scientific method. Maybe I'll forward it to you later. But yeah, science does not require the observation part. Science does not require cause and effect. You don't have to have cause and effect in order to have science. That's just those two in particular. The other one is natural. It has to be natural. Those are the three. Okay, that's good.
I don't agree with the natural the natural part. I think that we can use unnatural means to try to create an observation. I'm not one of those that's part of the control and variable process, right? You have to be able to manipulate it somehow.
Yeah, and that's all fair. Other than that, it's pretty good, and I agree with that. Let me do one little last thought experiment with you. Let's imagine we wake up with no knowledge of anything tomorrow, and we look out at the sky, and we see the sunrise, we see the sunset, we see the moon and the stars going around us. I think the reasonable conclusion is that the Earth is, basically flat. It obviously has hills and valleys, but no reason to believe it's a giant ball, and no reason to believe it's rotating. I think those objects are rotating in the sky above us, and that's a natural, normal conclusion. I think that would be our logical conclusion. Would you agree?
Sure.
And changing away from that conclusion would require some further evidence.
Sure.
I mean, if somebody came to us and said, no, actually, the sky is still, you're spinning, we'd say, okay, I have no way to disprove that, but you're going to need to provide me some evidence. You agree?
Yeah, absolutely.
Okay, and so this fellow who says, no, it's a ball, he pulls out a cell phone and dials up on FaceTime and shows you somebody in another country far away. And that person says it's nighttime. And you say, no, it's daytime. They say, no, look at my camera. There's the sun's not there, right? It's dark. No sun. At that point, wouldn't the logical conclusion be, well, I guess it's not flat. That somehow the sun is down for him and up for me. And therefore, the logical conclusion is I have been provided with evidence that it's round. I should accept this new evidence and change my a priori beliefs. No?
So in that particular scenario, I kind of think it has more to do with the framing. I think if someone came to you saying that, hey, this means that this is proof of a ball, then I think that you could definitely see it as that way. But if someone didn't tell me that and they said, hey, the sun is it's daytime over here when it's nighttime over where I'm at, I would simply assume that the light from the sun is not over me. It's like there's a local light, right?
Well, it's not just the light, it's the sun. I mean, you can't see it because it went below the ground. We watched it go down, right?
Well, the way that I see it is that
it's not the light doesn't reach here. It's that glowing thing is below the ground. We saw it go down.
Well, that's very simply a matter of perspective. I mean, regardless of if you want to believe that the world is round or flat, as things move away from you, they're going to go down towards the horizon. And then when you actually have things on that horizon, like hills, mountains, topographical features, the bottom of things that are in the sky are always going to be the things that disappear first because that's what merges with the horizon first.
Okay, so just back to our little thought experiment. You would say, no, that's not sufficient evidence for me to change my previous belief system that I just woke up with today. It was just my gut feeling because, I had nothing better to go off of. But the moment somebody gives me something better to go off of, Your response is, no, that's not good enough.
But again, with that particular scenario, you're saying that is the only, it's pretty much like an all or nothing, right?
No, that's not. Well, this is really what I'm trying to get at. Why are you characterizing it as if it must be an all or nothing? Why isn't that's a better explanation than what I had? Why isn't that sufficient?
Well, again, you're just saying that it's a better explanation. You're saying that the better explanation is that the Earth is curved. You simply just don't agree with the notion that the light won't reach us once it gets to a certain point. So,
No, I specifically pointed out that I'm not talking about whether the light can reach us. I'm talking about whether you can see that thing that was in the sky earlier has literally, you watched it during the entire day because, you're brand new on this Earth. This is new to you. So you watched this glowing ball go across the sky and go down and go below the horizon. You watched it do that. You didn't watch it shrink into the distance. You didn't watch it fade out. You didn't watch it circle over your head. You watched it go down. And you made the assumption at that time that the Earth was flat and that thing went down. But then somebody says, no, actually, it's not down for somebody over there. And then you go, maybe that's just perspective.
no, it's not even a maybe. It's you can easily demonstrate that things like that can be perspective. I mean, you can see this with clouds as things move away from you on a flat plane, and it
Okay.
merges in with the. It's not like a.
Okay. So what I'm getting at is, why is your previous belief that you started with on day one of it's flat? Why are you clinging to it? Why aren't you just as willing to jump off of it? I just made that up yesterday, right? I was just born yesterday. I just made this flat Earth thing up. I should be ready to just accept some other explanation. Say, oh, well, that's a perfectly good explanation. Yeah, maybe that's right. But that's not where you went. Why is that?
I would say, again, in that scenario where I know nothing at all, right?
Right.
I would be willing to accept it as a possibility. I didn't say that I wouldn't accept it as
Okay.
a possibility. Where the contention comes in is you want me to accept it as a better possibility, right? And I don't see enough reason to do that. I see it. You could even say it with equal information and no information about anything that's happened in the world. You could even possibly call it an equal possibility, right? But
Okay.
the reason why I tend to cling, and we're going to dive in a little bit to the conspiracy world, obviously. The reason why, with the current information that I have, why I would still, it's a little hard to shuck that bias, is because there is a ton of propaganda and spoon fed information from governments and systems that historically have not had our best interests in mind.
Yeah,
So there's a
that's
bias.
fine.
There's definitely a bias.
So you now have a bias to disbelieve the narrative.
Absolutely.
Yeah. Yeah, and that's what it comes to. I would also invite you, as a presumed seeker of truth, to check the statement that you just made, which is that you can demonstrate that perspective could explain this. I invite you to check that. As someone who literally teaches college students how perspective works, I'm telling you to check it, because that statement's not going to hold up. Just check it. Just learn a little bit about how perspective works. Just the baby steps of how does perspective work, and recycle that statement again, and come back to me with whether you've changed your mind about how good that evidence really is.
Is there something specific that you feel that you could point me towards that can help me with that?
Well, I mean, when I first got started with this whole like flat Earth thing, like one of the very first things, probably not the first thing, but one of the earliest things I ever did was I tried to organize a bunch of flat earthers to participate in an experiment with me. The experiment was, the premise of the experiment is, As something goes into the distance, it gets lower and lower towards the horizon. At what distance does it cross the horizon is the question. The question is, at what distance does the sun go below the horizon because of perspective? I would like you to answer that question with an experiment. And the experiment would be, just take anything. Like I use, as an example, I use Legos. Anything that's all the same height, regularly spaced apart, and take a picture looking along it. Look along that thing, and then measure the apparent height on your photograph. Measure how high each one of those things is and make a graph of it. Just graph height versus distance, and then continue that graph until it crosses the horizon. When it crosses, the height of the object must be 0. Like, how far away must the sun get till its height above the horizon would appear to be 0? Do that experiment and come back and tell me what is the distance at that when that occurs. It's very practical, very hands-on, very learning, very real world experiment that I think everybody can do. Costs nothing. You can use street lights. Just take a picture of a row of street lights. You can do Legos.
And we're obviously going to assume very minimal optical aberrations from the atmosphere.
Right. I think that's the assumed starting point, right? I mean, we're talking about, right, the whole thought process that I'm going through as a brand new caveman, right, is I'm going to base everything on what I observe. I'm going to start with the assumption that everything is very simplistic, and only go to complicated if somebody gives me some, evidence to do that with, right? So I agree. I'm going to start with flat. The Earth is flat. The sun goes around us. Until you give me something, a reason to complicate that, I'm sticking with it. As soon as we realize the sun is not above the entire Earth all at the same time, I said geometrically that means the Earth cannot be a flat plane. It's just literally not possible. And so I thought that was enough to complicate the model and make the model into a sphere. But you said maybe perspective explains it. And I agree. Maybe it does if you don't know anything about perspective, right? Or if you don't teach perspective, right? I dare say the kids in my class, coming into my class, they don't know that that's not true. But on the way out, I hope they do, right? Yeah, just do that experiment and you tell me how far away would the sun have to be on a flat Earth for it to visually appear to cross the horizon, assuming no atmospheric effects. And then, when you come back with a number, then maybe we talk about atmospheric effects.
Nice. Yeah, I actually really like where that can go, because if you can do that, then you can start ascertaining the sun's position over the Earth in both models, and you can start seeing which one matches. So yeah, I like where that can potentially go.
Yeah, just go with that. Just start real simple. Do one thing. Yeah, I know you're on YouTube like all the time, probably, but find a little time to just do that. And if you want to promote it, like get together a bunch of your fans to do that experiment together. Everybody do it. People from both sides, like clear your mind, clear your brain of any preconceived ideas, folks. Just do the experiment and tell me what the results are. I had literally 0 flat earthers do the experiment with me. Well, that's not true. I don't know if Eric's watching, but Eric did the first half of the experiment with me. Eventually I did find somebody willing to try the experiment, and he did it. So you can be number 2.
Maybe the math's just too hard, man. I don't know.
Well, that's just it. There's no math. It's line up Legos on a table, take a picture.
I'll scale it.
And then just measure the pixels. This is what I'm asking you to do. Measure the pixels from the top to bottom of the Lego, of the first Lego. Okay, that's 123 pixels. You write it down. Next one, 87 pixels. You write it down, right? You just measure each one. And then you plot those on a graph. And you can use paper and pencil, or you can use like a spreadsheet to just plot those on a graph versus like the first Lego, second Lego, third Lego, fourth Lego, right? Just do that and make your curve. And I think you're expecting a straight line that's going to go straight down towards the horizon, or go straight down towards zero. Zero height would be when it hits the horizon. And so if you just take a ruler and extend that straight line, you'll see where it crosses the horizon. And that's how many Legos out you'd have to go in order to get that horizon.
Right, but the hard part comes in translating that into real life, right? So,
well, it was real life.
No, I mean,
Legos are real.
No, I mean, that's not what I meant. I meant, okay, so the Legos are going down at this rate, right? And so we can estimate that it's going down by this many pixels, right? So then taking that and then going to the sun, taking a picture of the sun, doing the same type of experiment, but then trying to figure out the amount of distance for the pixel.
We may have to, we may come up with something like maybe Legos vanish at 100 yards, but something larger like mailboxes, we have to go out to a mile, and maybe, right? Maybe there'll be some other relationship. We'll have to dig further before we learn that. Although when you do the experiment, you'll learn the lesson I'm hoping you learn, which is that it is not a straight line. It never gets to the horizon. That's the lesson you're supposed to learn, is that your understanding of perspective was wrong. Do the experiment and see what perspective really does.
So I have a similar experiment now. It's more of an observation since it doesn't have measurements, But what it is I take a Burger King cup. I have my camera positioned over my flat countertop. The counter's like 7.5 feet long.
Okay.
And the Burger King cup starts at the back of the counter up against the wall, and I slide it up to the camera, and then I slide it back. And what you find is that the red line that's on the bottom of the Burger King cup will actually merge into the you can actually see the Burger King cup reflection in the countertop. So you can actually see that red line merge into itself and then completely disappear in the distance. And you can see it go both ways. The line comes into view when you move it up towards the camera, goes back out of view over this flat surface. Now, again, I know that doesn't have any like actual measurements behind it, and maybe I will still see that relationship of the curved line, the relationship of how fast things sink.
But the cup on the table was enough to convince you that the bottom of the cup is being obscured first.
Right.
And the science folks tell you, no, it isn't. You can create experiments that do that sometimes. Sometimes yes, sometimes no. The table may be curved. Is the first thing to check. Is the table curved? The next thing to check is, and this is the really the hard one. When your camera is very close to the table is out of focus, right?
That's true.
So if the table is out of focus, that means the table is blurry. What does blurry mean? It means part of the image of the table is smeared up away from the table.
So the part that's smeared, it's actually, if you I did it 3 different times, and if when you raise the camera up, you do get a little bit less, of course, but that's just obviously a function of height of the observer. But the thing is that the blurry part, the part of the table that's out of focus, is actually, well, you can see where that's at on the camera. It's like the very bottom line. There's a few things in doing that experiment that I found challenging, one of which was actually trying to provide accurate scale. Now, I didn't do the math for the scale myself, but I did have Globers from TikTok help me with it. And we basically came up with a figure that on a 7.5-foot table, you would need to have the camera height no more than, I believe it was months ago that I did this, but I believe it was no more than 7 centimeters. It was the really, really tiny one. Really, really small lines. It was almost nothing. You basically had to have your camera resting on the surface of the table in order to have it be as if you were a human standing on the earth
Right.
and looking out over a distance of, I can't remember exactly how many miles it was, but it wasn't like you were looking over the whole earth, of course. Uh,
Right. But so here's what I propose. And when I've done similar investigations with other flat earthers before, um, uh, instead of putting it directly on the surface of the table, and actually Jaron suggested this. It was really ironic. Jaron suggested it while he was criticizing me for doing it, which it was just odd. But anyway, I think he didn't understand what I was doing. Instead of putting them directly on the table, raise them up on something. I used cups. I used a pair of yellow cups that were identical cups. And then my two observation objects are placed on the cups instead of directly on the table. So that way I can get the camera as low as I want without hitting the table. So now the table is not part of the equation at all. I'm just looking straight along the cups. And then the question would be, now, as you move the cup backwards, does the cup appear to move up and down as you move the cup forward and back? And that would be an investigation you could then do to try to learn more about why the bottom of your cup vanished in your experiment. Because again, it did. I'm sure it did. I've never been able to reproduce it myself, but I've seen other people that have shown that in their experiment, for some reason, the bottom of the object seems to vanish first.
I think it has to do it might actually have to do with the scaling because you do have to move it back quite a bit in order to even replicate a couple miles. So it's
Yeah, I've done some, and what I found mostly was that focus was a huge factor. I found that focus was huge. I also found that the brightness and contrast was very significant in trying to reproduce that, but I never really was able to reproduce the effect that you're describing. It doesn't mean it's not real. I've seen people do it.
it also might have to do with the size of the lens of the camera that you're using. Because
Yep.
if you are trying to get like an observer on the ground, then if you're using, let's say, a full size Nikon camera lens, the top part of the part that's capturing light can be, several inches above the start point. So the way that you would look at it, to put it practically, is you would basically be a giant eyeball sitting on the earth, trying to view things like that. It would be a little bit different. I'm not sure exactly how different, but I know that it would be. So I try to use the smallest camera that I can. Um, and I've even speculated what would happen if you use like a micro camera, like one of those like really, really tiny ones because that would be
Yeah,
what
that
you
might
have to
help.
do to get like a human to get like something close to a human eye or a human camera lens.
Yeah, well, what I suggest is raising it up. Just put it, I think Jaron said put it on bricks, put it on a brick, and that way the table will not interfere physically with the camera, and you can literally then put the camera below the level of the table and see if that has anything to do with it. And then what you can do is investigate my hypothesis. My hypothesis is that the light from the distant cup to the camera traveled in a straight line. And I think that's everybody's starting point, is that the light traveled in a straight line. And as you get farther and farther away, the light should still be traveling in a straight line. And if you just make that one starting assumption, like that the light travels in a straight line, the result you get is perspective. Perspective is literally light travels in straight lines, and that is perspective. So to do that and then verify, is it true? Like, does maybe light doesn't travel in straight lines? And then I think the next thing I would want to do is raise the floor up towards the cup. Like if we line up the two cups and we line up the camera, so it's right there where the bottom of the thing is lined up, then if you bring a floor into the image, how does that impact the cup? How does that make it change? Is there something about the presence of this? Does the presence of a floor cause the light to bend? Because isn't that what you're saying? Is that something is making the light bend?
No, it's more. It has more to do with diffraction limits than anything. It's more like the light from the objects that is closest to the ground or closest to the horizon is going to be easier to become obscured due to the other light sources, or the other things that the light is bouncing off of. Another easier way to explain it would be that things contrast off of the sky much easier than they do the ground. And
Yeah,
so
that's true. The contrast is one of the things that I definitely highlighted. I would caution you against using the diffraction limit phrase um, because you're opening yourself up to be asked, what is the diffraction limit? Please show me the equation because it's a known thing. And obviously, that's not your gig, right? You're not going
right,
to want to do that math. And trust me, you don't want to because it doesn't support you. Right. So
I'm actually, again, I'm not one of the ones who's I'm not one of the ones who's like trying to hang on to a certain world position. I'm actually
okay.
in the pursuit of truth. So wherever that leads me,
Well, all right. Then
if that
if you're curious, yeah, I did a video on diffraction limits. I did a whole series, I think, on diffraction limit. It doesn't help you.
awesome,
It's not the diffraction limit.
yeah, well, I definitely like to check it out.
Okay.
I definitely don't. Again, anybody who's running from things that challenge their world presupposition is definitely not being skeptical. Definitely not doing it right. You can't call
I
yourself a
agree.
skeptic and not challenge your worldview. So
I agree with that. I think that's really key. So I'm excited about it. I think, I mean, like I said, I've seen videos where the bottom of the object appears to be obscured, or the object isn't tall enough, or blah blah blah. These things I've seen them. I haven't been able to replicate them, but maybe it's something I'm interested in. Why don't you, and I think that's an opportunity to do real science. Like, do a science, get out there and do a science. Like, try to find out why this is happening. Find out more. What are the controls for it? What is the independent variable that makes this occur? Right. I think that could be really cool.
absolutely, yeah, I completely agree. So yeah, you've given me a lot of information, a lot of stuff to chew on. So I definitely appreciate it. I do just want to go ahead and let all my fans know that no, I have not converted. I've not been, I've not been convinced that we're on a flying space ball, flying at all these different vectors, hurtling through space. Even if I yield on every single point that was made today, it still wouldn't mean that you can have gravity and it not be pulling things into spheres. You can have that same force, that electrostatic force, be pulling things down, be affecting the air, and make it possible to maybe not have a container. I don't know. I do know that this is stuff that we're all investigating. So I definitely appreciate Matt. I can science that for taking the time, having me on kind of last minute. I kind of just sent him an email after I missed the AMA to try to jump on and get some clarification. So I definitely appreciate that. I look forward to getting those diffraction limit links. And anybody else, I saw some people in the comments were saying they'd like to have me on or whatever. I'm making the circuit, so by all means.
Yep.
Uh,
There was a request. Do you have a Discord?
yeah, actually, it's just starting out. It's not very popping at all, but I am on Discord. Let me see if I can pull up what the heck that was. The better place to find me at is going to be Telegram, though, just to be honest.
Yeah, I was on Telegram for a little while.
I like it. It has a lot of capability. You can have unlimited storage, send way bigger files than you can with email.
Okay, I'm going to throw into the chat some links. There's a playlist for the Rayleigh criterion, the diffraction limit, as it were. So if you're interested in that one, and then let me try and dig up the perspective videos. My perspective videos are so old at this point that the quality is crap, but you know, this content's still good.
It's all about the information, right?
Yep. And so can we put in here your Discord link, or can you throw that in there?
Yeah, let me I'm actually, because I've never really used it, so I'm a little bit embarrassed to say that I'm having trouble finding it.
Okay, yeah, I'm right there with you. If you click on your own name, let me see, let me just do this. Click on your own name, which I think is the bottom left.
I'm here. Okay, got it. Troubling Tribune number 5187.
And then if you see next to your own name, when you click your own name, the little thing pops up, and then there's a copy button next to it.
Not seeing that.
Not seeing that?
Copy username.
Yeah, that's the one.
Okay.
And then you can just hit paste in the thingy, and that should work.
Sick. Thank you for walking me through that.
All right. Yeah, I just found it earlier today. Okay, and here's the video about the perspective experiment that I'm asking you to follow along with. And then on your own, maybe you could take it to the next level and try to investigate whether there's some kind of obscuring at the bottom effects that you can come up with by doing experiments. And the last one I want to throw at you is the derivation of perspective. Just what is perspective? Why is perspective? Yeah, I like that. It's what I should call it. Instead of calling it what causes perspective, I should have called it why is perspective. In fact, I think I'm
more compelling.
I'm going to rename it right now.
I'm gonna shout out Nuba. Nuba's one of the people who's always on my videos. He says I look like I've been hit by a bus. I need to get some sleep.
Yeah, go get some sleep. Go get some sleep. Anybody else in the chat want a last statement before we close it off? No, I think we're good. So it was a great talk. Really refreshing. Love to have you come back sometime. There's a couple of things I wanna talk about sometime with people who think like yourself. Would love to have you come on and maybe on a panel or something we'll put together. It'd be great.
Nice. Get all the gotcha questions lined up and ready to go.
Yeah. Get the gotcha questions. No, I mean, I don't want to do gotcha. I think that's been done to death, right? It's been done to death.
Yeah.
What hasn't been done maybe enough to my satisfaction is to delve into why you think different than I do, and where is the origin of the differences, right? Because we both see the pressure gradient, right? Like, for example, we both see the pressure gradient, and I conclude, therefore, we don't need a container. You saw the pressure gradient and said, yeah, it's got to be a container. Something went different in there, and I'd like to dig into why that is, and what can we learn about each other by exploring that.
Yeah, that'll be really fun, and that's really good for the audience to get good perspective on how both sides of the fence think. It's something that's really, really important, and I agree it doesn't happen enough. If it did, the powers that be probably don't want that. I think that regardless of what you believe in, I think that there's some division that's been propagated throughout every sector. So whatever we can do to bridge that gap, I'm all for.
Yeah, for sure. Absolutely. All right. Been great. And I guess we'll talk again sometime soon. Good night,
Absolutely.
everybody.
Good night. Thanks for having me.